Hi, my name is Jake Weller. My senior design project was a spackle/drywall inspection tool called the Defect Detective. Before designing the device, some research was conducted to search for existing products or patents that are similar in concept to the inspection device. One such device is one called the Ergolis Inspection Lamp by Belmore Tools. It is essentially a light bar attached to the end of an adjustable arm. Another device out there that was found during patent searches is the Festool Surface Control Light. Very similar design, however on a tripod stand. While these tools may very well do the job of drywall inspection, they have a few problems with accessibility. The Ergolis inspection lamp cannot be bought online, as it is near impossible to find a retailer that actually sells them. And the Festool Surface Control Light is listed at around $500 on most retail sites. The goal of my design was to create a simpler and more affordable product that will get the same job done. A product that any consumer can purchase and use to do inspection in his or her own home or workplace. After doing the preliminary research and thinking over the objectives of simplicity and affordability as mentioned before, some basic design requirements were decided on. The design requirements are as follows. The components of the housing were to be injection molded and needed to be designed to be easily injection molded. The device itself would need to sit flat against the wall to provide an optimal light beam angle to do proper inspection. The design itself needed to be simple and affordable, and the design overall needs to be strong enough to ensure its integrity through its typical use. The device would have to work similar to this diagram, being positioned close enough to the wall to produce the proper angle for the light beams. Final consideration was what light source would be most optimal for this kind of device, as well as the optics. In considering the kind of light source, it was found that LEDs utilizing total internal reflection would be optimal for this device. According to LEDIL.com, these lenses are rotationally symmetrical designs, which give a round light distribution. In other words, the lenses force the light out in near straight beams. To ensure that requirements were met, a large portion of time for this project was dedicated to designing the components of the housing, as they were the main designs being created. The housing was originally divided into a bottom and top piece. Doing a bit of research led me to an information PDF from the RTP Plastics Company about designing injection molded parts. As seen, the housing is of a circular design of about 8 inches in diameter with a wall thickness of 0.15 inches. The top housing component was given the most design time. It would incorporate the handle and the space for a power switch in order to minimize the amount of parts in the assembly, keeping the trend of simplicity. The next area for consideration was how the components of the housing were going to fasten together, as well as the rib features on the inside of them. The lip and groove feature designed in SolidWorks is shown and is present around the perimeter of the circular housing. The components of the housing are also fastened together with 18-8 0 size Torx rounded head screws. Rib features can also be seen that exist to enclose both the heatsink that the LEDs are adhered to and the power supply for them. These rib features are also present in the design of the top housing to properly enclose these components. While contacting a company called Eccentric Molds for pricing on components of the housing, it was determined that the top housing component could not be properly injection molded in its current state. The top housing was redesigned to be 2 separate parts, connected with an identical lip and groove feature as shown previously. A few minor design changes were also made at this point in the process, including reducing the length of the lens plate from 5.25 inches to 5.1 inches to allow it clearance to fit inside of the lens, Also, the design originally called for Delta PT 5411 screws, but I quickly found out that these screws are difficult to find, while the Torx rounded head screws are widely available and perform the same function. The material selected for the components of the housing was polystyrene. After some research was conducted, it was determined that most modern flashlights and handheld light devices are constructed of this material. It is also commonly molded with a wall thickness of 0.15 inches, which is the thickness these components were designed with. The heatsink and reflective plate for the LEDs would be constructed of 6061 aluminum, as this material is cheap, easy to manufacture, and sufficient for the needs of these components. Finally, the lens that covers the LED opening would be injection molded as well, however out of acrylic. Acrylic is generally cheap and is a common clear material used to create lenses. To ensure that the components of the design would withstand the forces it would see in its typical use, a stress analysis was conducted. It was determined that this product would not only need to withstand the force of an average human leaning their weight against it, but also the force of an average human pushing against it with full force. A trip to SolidWorks forums determined that the force an average human could produce by pushing is roughly between 480 and 600 newtons. For the first test, 240 newtons was used, as this is half the pushing force and would suffice to estimate the rough force of a human leaning. The bottom face of the housing remains constrained, while the force is applied to the top face of the handle. It was determined that in these tests, displacement should not exceed 0.1 inches, and the factor of safety should not be below a value of 2. The components of the plastic housing hold up extremely well against the forces of an average human leaning against the handle. The maximum displacement is negligible at just 0.012 inches. It can be seen also that the maximum von Mises stress at the handle was just 1,186 psi, and the factor of safety exceeds requirements with a minimum value of 5.1. The next simulation test to be conducted was identical to the first analysis, aside from the force being exerted being changed from 240 newtons to 600 newtons, to simulate full pushing force being exerted against the top face of the handle. Again, maximum displacement is negligible at just 0.03 inches. Maximum von Mises stress on the top face of the handle didn't exceed 3,000 psi, and the factor of safety just meets requirements with a minimum value of 2. Hand calculations were done in order to confirm the results of the SolidWorks stress analysis. It can be seen here that hand calculations were done with the force on the handle being 600 newtons. It was decided that this was the more crucial test analysis, as it was the most extreme condition the device would face. Hand calculation results were quite accurate to that of the simulation stress analysis, with von Mises stress being 2,570 psi, while the simulation results were 2,967 psi. It is also important to note that the hand calculations were done omitting the cutout for the power switch in the handle. Calculations were also done as though the handle is a consistent cross-section, even though the cross-sectional area is very slightly tapered. This was done for the sake of simplicity in calculating the results. Here the pricing for purchased components can be seen. The LED components are all purchased from LED Supply. The power switch was purchased from Carling Technologies. Torx rounded head screws are widely available for purchase from McMaster Carr, and the round felt pads for the feet of the device can be purchased at any hardware store. Here the pricing for manufactured parts can be seen. The injection molded parts were all priced by Eccentric Mold and Engineering, while the aluminum components were priced by Midwest Steel and Aluminum. As is the nature of injection molded parts, producing a large amount of parts directly decreases the cost per part of manufacturing. This concept can further be seen by the break-even point calculations here. As amount sold goes up, profit also goes up exponentially. Selling the device at around $200 will ensure that profits are achievable while maintaining the original goal of affordability and simplicity. When it came to modeling the plastic components of the housing, it was found that the best approach was to model it first as one part file, containing multiple solid bodies. This became useful when making the addition of the lip and groove features on the components of the housing. All components of the design were made using basic solid modeling techniques. The experience gained from this project has been unlike anything else I have experienced in my academic career. The experience of developing a project from very start to very end is something I will take with me through my professional career as well. I am unimaginably proud of the work and effort I have put forth into this project, and can say that every hour spent on it was well worth the work. If there is one thing this project, as well as my time here in the engineering design technologies major, has taught me, it's that anybody really can do anything with a little hard work.